All right, so we have our second presentation on deep reinforcement adaptive computational processes. So take it away whenever you guys are ready.
Okay, so yeah, we are Team 28, and as Greg said, we're deep reinforcement adaptive computational processors, and I'm Andy Wu, and I'll
I'm
be working
Andre.
with I'll be working with Andre and Xintian, with project lead Dr. Vahid Tarok and project manager Dr. Yi Feng. And so just to go over sort of a background of what we're trying to accomplish when doing this in this project. So basically, when we're working with signal and signal data, the information comes packaged as like a sequence of points that we sample along the source signal. And if we say wanted to do operations like, for example, multiplication between signals, we would essentially need to reconstruct the entire signal so we could do the multiplication that way. But so there's two sort of methods of doing this. We could either sample extremely fast and basically get like the exact points along the signal so that we can just multiply them point-wise, or we can sample more sparsely and then use a numerical method, like say interpolation, and make a reconstruction. But doing this reconstruction, because it's not getting the exact points, will introduce some error from the numerical method. So in this project, we're essentially seeking, first of all, to decrease the number of operations or sampling operations that we need to do to get this reconstruction. And also we want to say if we have a fixed number of sampling points, we want to strategically pick these sampling locations so that the error that we introduced is minimized. And as sort of motivation and idea for how we can make this happen. Our goal is basically, first of all, to minimize like an absolute relative error. And that's, okay, I'll talk about this a little bit later. But we want to minimize like the error between the signal that we construct and the actual signal if we were to take it exactly. And some fundamental equations that give us this idea is like given below, where we see like the multiplication or the error of a product of the signal. And in the end, we get this result that the relative error of the individual signals will essentially add up to be the relative error of the product signal. And this essentially tells us that if we can somehow coordinate the signs of the relative errors at a given points and sort of try to get these guys to sort of cancel out and do a destructive interference type phenomenon, we can essentially lower the relative error of the product at those points and get this basically achieve our goal. And so a graph that sort of demonstrates this is here, where as you can see, the signal 1 error is plotted in the red dotted lines. The signal 2 is plotted in, the signal 1 is plotted in the blue dotted line. The signal 1 is plotted in the red dotted line. And the error of the product is plotted in the solid yellow. And as you can see, for regions like, say, this region at the end, the error of the product is actually in between these two signals. So that indicates that the errors of the individual signals are interfering and producing a lower relative error for the product. So that's kind of to show how something like this can happen. Okay. So Andre, do you want to talk about some of our models that we've used?
Yeah. So okay. So Andy has talked about the background and motivation, and right. So the motivation, just to recap, is that we would ideally use this sort of destructive interference. This will help with like lowering the relative error, and so in order to achieve this ideal version of destructive interference, we need models that can sample smartly, strategically, like sample in a way that is not like a fixed sampling schedule, like a uniform sampling schedule, but instead take into account of the knowledge of the terrain of the signal and how the signal will look like in the future, or at least like how the relative error will look like in the future. And so we have proposed, so we have all agreed on, and Dr. Yi, like we have talked about this, and we think that a reinforcement learning based agent will be the most promising way to achieve this strategic sampling. And there's two reasons behind this. One reason is that so in order to do this, we need to in order to like actually like one day make this like feasible realistically, we need to be able to like run our agent pretty fast. And that means that we can't have like 10 million, 20 million parameters in the model. That's just gonna be way too slow. So a reinforcement based agent, they usually take less parameters and they're more adaptive and they can learn online. So like a new signals come in, a reinforcement learning agent will be able to like kind of like learn like as the signal plays along and as it samples, it will make mistakes, but then it will correct those mistakes and then it will keep going and updating and maximizing its strategy. And that's why like a reinforcement learning based approach is better than a parametric statistical approach or a deep learning approach, because the later two methods will need to be trained more extensively, and that will take a lot longer than what like a real-time signals processing, this sampling will allow. And so that's like the two reasons why. And so we'll introduce like our reinforcement learning model or this like learning schedule that we have shown. Can you zoom in on the first part of the second column? Yeah. So the way we're gonna do this is that, so we have talked about this in our presentation, but reinforcement learning is like, it's not really a new idea. It has been around for like about 50 years, 60 years. Recently it has come into more prominence because we have this deep learning representational capacity that will be able to basically help reinforcement learning agent to do better. And so there's some key concepts in reinforcement learning. One of them is reward or return. Well, they're different concepts, but like we're treating them similar here. So a return is what the agent will try to do. So the agent will always try to go for the maximum amount of reward. So it will try to follow a strategy or a policy. It will do some actions, and it will try to go for this maximum amount of reward. And the policy will be some sort of parametric model that will be used, and the policy will be able to update it when the parameters of this model changes. So so the first thing that we need to do is that the reinforcement learning agent will need to recognize the signal terrain or the information at hand. And the way that we thought that it would be good is that we'll represent the signal as a time frequency 2D representation, as in a power spectrogram. So we have two signals, and both of the signals, we calculate the last part of the signals as the power spectrogram. And the power spectrogram will be the state that the agent will be able to see, and that this is more convenient than just using a 1D signal. Because using power spectrogram, we'll be able to use the power of the convolution neural network at CNN. So as you see, power spectrogram 1, power spectrogram 2 are the state, and the state goes into the CNN, and the CNN, after the CNN, we'll be able to, and then we'll have a policy. Then the policy basically will be able to select the next action. The action here is how it samples next. So a uniform action will be always samples like 10 milliseconds ahead of each other. So 10 milliseconds, 10 milliseconds. But since we're doing this strategically, we'll have the option to choose between 7 milliseconds to 13 milliseconds. And in a way that this will make the the sampling non-uniform. So we'll choose the action, and afterwards we'll calculate how the state action, like given the state, given the action, how the reward looks like, how the return looks like. And we'll save that into a pair of a state action return pair, the SAR that you see after the step. And after we got like a bunch of those SAR like step pair, we'll be able to train the CNN part of the model so that it will better represent, so that it will better represent like the actual return. So the key part of this reinforcement learning thing is that we'll need to use the episodes, the signals the experience we have so far in order to better inform the model of how it should do in the future. So we need to update those CNN parameters. And after those, we can do the prediction and sample location for next signals. And yeah, so this is the actual implementation that we did uses a Monte Carlo simulation. A Monte Carlo simulation is that basically you play a signal till the end. So you don't do any sort of online learning as it goes, but you play it to the end, and then you get all of those experience and use those experience to train your model. And you do that over and over again, play maybe 10,000 different signals, 20,000 different signals to see if there's improvements in the relative error of the new sampling strategy. So that's the reinforcement learning part. Yeah. And so why do we, so our project title is called Deep Reinforcement Learning. So reinforcement learning and the deep reinforcement learning. So I would say that deep reinforcement learning is what made reinforcement learning more popular with the AlphaGo and all of those things. And the reason why is because reinforcement learning, they use a tabular approach to tabulate those state action pairs. So they usually have a lookup table. So you see a state, you see an action, and then there's a return there. So like it's kind of like a dynamic programming table, if you think about it like that. But the problem that we have right now is our state is a spectrogram, and a spectrogram is like a high dimensional thing that lives in this sort of power spectrogram manifold, and that's not something that you can count. So it's not possible if you use a tabular approach. So you can make that into a lookup table. So the way that we do that, even with the CNN, is that we will try to use a parametric model to represent this huge lookup table. So think of that as a regression problem. And that's what we do with the CNN. And actually we can do better than a CNN. We can actually use more complicated deep learning model to represent this parametric part of this value function approximation. And that's why we call this deep reinforcement adaptive. And later on, we'll in the second part of the second column, we'll introduce a proposed reinforcement learning, a deep learning model that basically are more, that basically will increase the representational power of the model.
All right. So thanks for introducing. I think if we should sort of speed it up a little bit so we can get to the questions. But yeah, sorry about that.
Right. Okay. So we don't really need to talk about this too much because so I just want to mention that we have implemented this and we'll see if this works. So we'll go to the results now with Qingqian, and then we'll answer some questions. And if people are interested in this deep learning model part, we can talk about that later offline.
Yeah, for sure. So if you can zoom in into the experimental result portion, I'll quickly go through them so that we leave some time for questions. So as you can see, the first graph is after we implemented our Monte Carlo control model, we found that so if you look at the graph, it's a histogram of reduction of relative error. And on the x-axis are the percentage reduction of relative error compared to uniform sampling. So if it's positive, meaning it means that our algorithms calculated sample points, sample locations produce a lower relative error than the conventional uniform sampling. And on the y-axis is basically the proportion of the test signals that had this amount of reduction as compared to uniform sampling. So as you can see, there are certain signals pairs are able to get a reduction that is more than 0, meaning performing better than the conventional uniform sampling method. And very few, yeah, and we can see that some signal can even get until almost 20% better than the uniform signaling, uniform sampling. The second graph that we display here is we wanted to establish a baseline of how much using our RL algorithm we can reduce the relative error. So what we did was that we did a random perturbation search, meaning that we fixed the number of total sampling points the same as our in our RL algorithm, and we perturb each sample points by a little bit to see if we do it randomly and we search it for a lot of times, how much of the improvement can we achieve? So if you look at the graph, the shape of the positive direction is actually really similar to our RL model. You can see that, yes, sure, the maximum reduction of error can reach maybe 20–25% than uniform sampling. However, the majority of the signal pairs could only reach very, very little reduction. Therefore, it is really hard for us to achieve reduction that is more than the uniform sampling. So after this project, our next steps would be, we would like to integrate our deep learning model with our reinforcement learning model. And in order to optimize and further reduce our relative error, we also would like to implement the TD lambda model, which will help to converge faster and have a better improvement, we expect.
Right. I want to say one thing about the TD lambda model, just before we go on quickly, is the TD lambda model will have the ability to learn online. And the Monte Carlo is a simple implementation that will learn after and then the signal is played out, but TD lambda has the ability to be more adaptive and learn online. Right, keep going.
Right. The difference would be Monte Carlo is only updating the CNN parameters until the end of the episode, but TD lambda model basically updates every step according to a certain proportion. So it will learn faster, and also we can learn it on the fly.
Right.
So this basically summarizes our project, and we would like to thank our mentors and thank our Data Plus for providing us with this opportunity and providing us with a lot of support.
Thanks a lot. That was really nice.
If anyone has any questions, we're happy to take them.
Thanks a lot. That was really great. Again, I have plenty of questions, but I would love to hear from the audience as well. So I guess one thing is, while we're waiting for somebody for people to formulate their questions, is I guess how do you think that what you're doing would compare to something like an adversarial network, where you have maybe one network trying to fool or trying to figure out a signal that's going to maximize the error of your current CNN, and then sort of iterating in that way. So how would that be? How do you think a strategy like that would compare to the strategy you're using?
That seems like a great idea, but I think what adversarial, okay, so some sort of adversarial training will definitely make a model or a method more robust, because one of them is trying to come up with a signal that you cannot have any reduction. The other one is trying to use come up with a sampling strategy that make this impossible signal to have like a reduced error. And that's like definitely gonna make the approach more robust. But what we have right now is that we are using some sort of sinusoidal signal. So it's not sinusoidal, but it's like 20 to 50 components of different sine components. So think of that as something like a Fourier series thing. So like it has like a lot of randomness in its like frequency and the shape and all of those things. But it's definitely not as random as like a random, like a Gaussian noise signal, something like that. So that would be something to consider in the future, I think. The current strategy is that we hope that this method will work well in like the signals that we have provided so far, for like a more like a robust model that will kind of like hinges on if this thing will be able to like kind of like improve on the signals that we have given it so far.
Yeah. So basically you have this, you're sampling from this 50-dimensional Fourier space, and what you
something like that, yeah.
And so the difference would be trying to find the worst case in that space versus finding a typical sample in that space, right? right?
And also, like maybe you have noticed that there's only 4% of all of those signals that we have produced actually can have some sort of reduction. So there's really no need to use an adversarial network to come up with a signal that's impossible, because there's already a lot of signals that are pretty impossible right now. So the goal after this part in the future work right now is that we need to kind of like figure out like, okay, so can we have a model that will be able to work even with our signals? And then we can like go one more steps and think about what if there's a system trying to give you an impossible signal, and then that's like a later thoughts though. Yeah.
Yeah, cool. Thanks. Nathan Warren wants to know, is the code for this public?
The code for this will be public after we have compiled this into some sort of academic paper, and then we'll need to make the Git public. Yeah, but the code is mostly, so the code is not really that complicated. So the Monte Carlo implementation is pretty straightforward, and the deep learning implementation is also it's just an LSTM based model. Yeah.
So I was also wondering, there's a number of things that seem like this could benefit from, like, you know, I mean, one thing I would, so one thing you could ask is, why not just sample more frequently uniformly, right? But then that would lead to memory issues. It may lead to energetic issues. I was wondering if you had a particular improvement you were hoping for, whether it was energetic or whether it was memory savings, or whether this is just sort of, you know, all of those things. You're not really focusing on one of the types of improvements, but just something more generally.
Yeah.
Andy?
Regarding like the energetic, like this is something that we wanted to also improve upon, because as I sort of like grazed upon a little bit earlier, we talked about how like taking a whole bunch of samples, like sampling more frequently, would have energetic problems. And one way that we've been able to say lower the number of samples we take and therefore lower the amount of energy that we use is by looking at like the signals and sort of figuring out a way to estimate how fast we need to sample each to get information, because the rate at which we need to sample we need to sample a certain signal depends on the bandwidth of that signal. So if we can sort of estimate the local bandwidth, we can estimate how often we need to take samples, and therefore we wouldn't need to come up with like some like the max, like, or some generous maximum that and sample like much more than we need to. We'd be able to like determine this by, and when we figured out to sort of do this is to sample a signal very quickly, so we can get a very exact approximation like in a small time frame, and this will basically let us estimate the bandwidth and sample that signal according to its own bandwidth, instead of like say some generous maximum band limit.
Cool. So Ali was wondering what the sensitivity is to your model from noise.
We have not introduced noise into it.
Cool.
Yeah, as of right now, it's just it's many different just.
So it actually wouldn't be that worse if we introduce noise, because if you think about it, the noise will basically be high frequency components of a power spectrogram. So there's a lot of ways to use a low pass filter to just get rid of most of the Gaussian noises that we introduced. Yeah.
Would the CNN sort of naturally do that if it's already kind of naturally focusing in on the
CNN will be able to do that, but that will require like a deeper convolutional network. So convolutional neural network has been known to denoise pictures even without like specifically implementing a low pass filter or like a band limited filter. Yeah.
So I guess so turning back to the sampling problems, that are you limited at all in terms of how frequently you can take samples, just in terms of the physics of, you know, so, you know, I imagine there's some type of physical thing that happens and is there a lower limit on how quickly you can take those samples? And does your model account for that, or are you kind of putting constraint parameters on this, or are you just kind of leaving things free for now?
Great question. So I think I'll take this one. So
okay,
I think we're talking about the Nyquist sampling theorem here. So in signal processing, there's a Nyquist sampling theorem that says that if a signal plays on forever, so if the time is forever, it can goes on forever, and then we'll be able to use a Nyquist sampling rate, which is twice the maximum, which is twice the bandwidth of the signals, and then it will give you a perfect reconstruction of the signal. And so that will be, but then that theorem is limited because obviously we can't have a signal that plays on forever. So for any like realistic signals, we need to sample a little bit faster than Nyquist rate. And even if we do that, there's a lot of place where there can be some sort of reconstruction errors there. Mm-hmm. So I guess like in our paper, in our project, we're using, we have tried differently. So some of the times we're just using Nyquist rate, and sometimes we're using like a little bit faster than Nyquist rate to see how it goes. I think Qingtian will be able to explain this better.
I also think that in most traditionals, like when people are doing the source sampling, they generally sample very slightly higher than Nyquist rate, maybe like 1.1 times the Nyquist rate or 1.05 times the Nyquist rate.
Cool. Yeah. And sorry, you can finish your thought.
No, you can go ahead.
All right. Yeah. So just to sort of summarize what Andre and Andy mentioned, our project's objective is to minimize the trade-off between the accuracy or error and the energy consumption. So we want to, within a certain error tolerance, sample as little as possible and sample strategically so that the overall error is smaller. And that therefore we would want to try sample less, have a more limited sample. And we know that we should sample at least at Nyquist rate or above. So we ran some experiments slightly below, at Nyquist rate and above Nyquist rate. And we observed that the relative error, the overall relative error is actually pretty similar. And that's why we decided in our training algorithm, we used Nyquist rate at the minimum.
Yeah.
Yes.
Thanks. So great. So thanks a lot. This is great. If anyone has any questions, any further questions as we transition into the next group, feel free to chime in or put them in the chat. But let's at least make sure that the next group can share their screen and the slides look good and everything. So thanks a lot.
Thank you.
Yeah.
Thank you.